Okay, so today we will continue with stochastic integrals because stochastic integrals are rather hard, so hard that probably they are in some sense easier to work with than ordinary integrals. So they are so hard. So we continue with stochastic integrals and stochastic integral and properties. So let's recap some properties, and we will study a lot of problems, I think, because practice is important here. Okay, what we have studied that under mild technical conditions, we can easily calculate expected value of stochastic integral from 0 to t au dwu, and we have stated that this value is 0. So that first fact that is very useful. So if you represent some process as a sum of stochastic integral and ordinary integral, that's easy to calculate expected value. Second point, the variance of stochastic integral may be calculated as expected value of ordinary integral with du and not dwu. Third property, it is not related to stochastic integrals, but we will write it here. Expected value of integral from 0 to t, something like bu du, just integral from 0 to t, expected value of bu du. Just because integral is a sum, and expected value of sum is often the sum of expected values, hence we may interchange in many applied cases, we can change the order of integration and expected value. And the fourth property that has a special name, Ita's lemma. We have stated Ita's lemma in short and full form. So Ita's lemma in short form. If xt is some function of t and wt, then dxt is dh with respect to dt times dt plus dh with respect to dw times dwt plus 1 over 2 d second derivative of h dw times dt, and fourth, that's the correspondence between short notation and long notation. Correspondence between short and full short notation and full form. So when we write dxt is at dwt plus dt dt, we really mean that, so that's an abbreviation, so that's just a notation, be careful. Objects in this notation are meaningless per se. So dxt does not exist, dwt does not exist. we really mean that xt is x0 plus integral from 0 to t au dwu plus integral from 0 to t du du. So these are five paths that we often use to calculate some properties of random processes in continuous time. Once again, let's recap. The first property is very easy. The expected value of stochastic integral is 0. The second property, name it as isometry. That says how to calculate variance of stochastic integral. The third property has nothing to do with stochastic integrals. There are no dw, but as the second property suggests, sometimes we need to calculate expected value of an ordinary integral, and the third rule says that we can interchange the order of integration and expected value. The fourth most, the hardest one. So for dxt, you need the derivative in analog of Taylor expansion. We need second order term. And rule number 5 just says how to go from short form and the full form forth and back. Okay, now I think we are ready. And I will present some, I will solve, I think, some problems from stochastic calculus course in ISEF master program, because it's a crash course for newcomers, and we are doing a bachelor course, but it's comparable to the level of difficulty of master crash course. So the level of problems from the exam on stochastic calculus is appropriate to our knowledge. Okay, so let's calculate something more interesting. Yeah. Okay. So that's example exercise. So now we will do a lot of practice. Okay, I will make a screenshot. That's from the exams collection. Okay, consider the Vasicek interest rate model. Vasicek interest rate model. In the Vasicek interest rate model, the interest rate is modeled by stochastic differential equation. dRt is equal to 0.05 minus RT dt plus dWt. R0 is 0.07. And so these stochastic differential equation describes the behavior of interest rate over time. That's a simple model, not very complex, but used. That's a real model for interest rate. In this case, the interest rate is stochastic. Yeah. So this is T, this is RT. It starts at 0.07 and it fluctuates randomly. Yeah. And our goal in this exercise to first recover the full form. First, what is the meaning? So recover. So point A is very easy. Recover full form with integrals. Full form. The second question calculate BT, that is expected value of interest rate at time t. Find this BT. Okay, so first let's recover the the true meaning of this line, yeah, because we understand that DRT is not a random variable, that's just a shorthand notation. So the first question is easy. We say that RT is R0 plus integral from 0 to T 0.05 minus RU du plus integral from 0 to T 1 times dW, or in this case, we can easily calculate some integrals, replace R0 by 0.07. That's the integral. We know it. It's one that we have in our integration table. Yeah, our integration table is very, very small. We have basically 3 integrals there. So this is minus 1 times W0 plus 1 times WT, because once again, the meaning of this stochastic integral, we interpret the first function as a quantity function. We interpret first function as quantity function. The function after the letter D we interpret as a price function. So if you have one apple, you buy it at time t equal to 0 with the price W0, and you sell it at time moment t when it has the price WT. So that is your net profit. Okay, so basically the short form hides the long form with integral plus WT. So that's the behavior of interest rate in Waschik interest rate model. Obviously, parameters in real life are estimated. So instead of, so here we have something like 0.05, 0.07, here we have 1. So in real life, instead of these numbers, we can estimate them from prehistory and make some calculations using this Waschik interest rate model. But that's an incarnation of Waschik interest rate model with particular parameters. Okay, now B, what is the behavior of expected value of RT? B, let's calculate expected value of RT. So let's go back, let's recap quickly our properties. So we have only 5 properties. We have used property number 5, the correspondence between short form and full form. And the 4 properties, we need, I think, the third one, and the expected value of Riemann integral, of ordinary integral, that we can interchange the order of integration and expected value. And in our case, we will have 0.07 plus integral from 0 to t expected value of 0.05 minus RU du plus expected value of WT. If you remember the properties of Wiener process, what is the expected value of WT? Remembers? Anyone? What is the expected value of Wiener process?
0.
Yeah, that's 0. So if we say that BT is just expected value of interest rate, then BT is 007 plus integral from 0 to t 005 minus BU du. Now we have a non-stochastic differential equation. That this is really a differential equation. We can calculate the derivative d of the left-hand side of the right-hand side with respect to dt. So we will get b prime t is equal to 0 plus, when I take the derivative of the integral, I will just get the function that I integrate, yeah, plus 005 minus bt. If I take the derivative of the integral, that's easy. If you just calculate the derivative of the integral, you will get the function inside the integral. So I have the equation b prime t is equal to 005 minus bt. And we can solve this differential equation. How can we solve this differential equation? How? Any ideas how to solve it? Okay. Basically, you can separate variables. So maybe if you know how to solve linear differential equations, we can guess the answer. So basically, I know two strategies how to solve it. Either we can separate variables. Either if you know there are, because this type of equation, linear differential equation, is very popular. It arises here and there. So we can recognize linear differential equation, and there are answers for this type of differential equation. Recognize linear differential equation. Probably from the absence of answer, I will prefer the first way. So it says dB over dt is 005 minus b. dB divided by 005 minus b is just equal to dt. I add integrals, and I got t plus constant, and here I get logarithm of absolute value of 005 minus b, and hence I have the link between between b. Basically, I say that 005 minus b is some constant multiplied by some other constant. Let's say g multiplied by exponent of t, and hence bt is equal to 005 plus some other, how to name it, c, d. Ooh, I need more letters. Or maybe minus d times exponent t. Yeah, I will be satisfied with one letter. Okay, so that's the behavior of my interest rate. And I can easily recover D. Yeah, I can easily recover D because I know that B0 is expected value of R0. It's expected value of, as far as I remember, it was 007. 007. And hence that's 007. And 007 is just 005 minus D times 1. And D is minus 002. And the final answer, BT, is equal to 005 minus 002, no, plus 002 exponent of t. And that is the expected value of interest rate in the Waschuk interest rate model. And hence, I can draw it. I can say that this is expected value of RT. It goes to 005 in the limit. Oops, sorry, I've missed -1 somewhere. Yeah, I missed -1. Sorry. When I find minus here, so it's minus there. And it's minus t there. Because I have minus inside the denominator, I will have minus before the log, and I will have minus everywhere, and I'll have minus everywhere, and my expected value will tend to 0.0005, and the real function RT will randomly fluctuate around this expected value, so somehow it will fluctuate, and so sometimes above this expected value, sometimes below this expected value. So we have solved our unexpected values. Yeah, we have solved our first simple financial model used to model interest rates, and I think that's already a good reason to study stochastic integrals. Any questions? Shall we continue with more questions? Okay, let's continue with questions. I will choose some problems that are at our level of mastery of stochastic integrals. Oh, that's also a good exercise. Also a good exercise. Yeah, here it is. Okay, so we have WT, that is winner process. And the question is to find a expected value of W5, W4 given W4, and to find variance of W5, W4 if we know W4. Okay, let's go here. If we know W4, we can take it out like known constant, x known constant. So it just goes out. So this guy will go out of the expected value. W4 times expected value of W5 given W4. Now we use that future value can be represented as current value plus change. So we use the trick future value is equal to current value plus change. So simple trick, it works. W4 is equal to W4 plus change, W5 minus W4. From mathematical viewpoint, I have done nothing. I have just added and subtracted the same value, so I haven't changed. This goes out the expected value, W4 times W4 plus expected value of the increment. And the advantage of this still decomposition is that the increment and past value, they are independent. So that is the advantage of this simple decomposition. Independent, hence I can omit the knowledge I have if my knowledge is independent of what I'm trying to forecast. Then I can omit my information, and I will have expected value of W4 times W4 plus ordinary expected value of W5 minus W4. And we know from assumptions of Wiener process, assumptions of Wiener process, that WT minus WS has which distribution? Who remembers?
With zero mean and variance T minus S?
Yeah, exactly. So the expected value of this difference is 0, and we have W4 squared. Let's continue with variance. Yeah, you are completely right. Basically the same trick will be used. W5 times W4, if we know W4. We say that it is, we take it outside, but when we speak about variance, constant multiplied, fixed value multiplied by random will go outside with square sign. And inside I will use the same trick of decomposition into known and unpredictable parts. So I will get W4 plus delta once again. Now inside variance I omit this value is known fixed value. I remove it because it's known fixed value. I'm W4 squared times variance of W5 minus W4, that is independent part. Independent. And it is W4 squared times 5 minus 4. We have the fact that this difference has variance T minus S. And T minus S, in our case, T is 5, S is 4. Okay, we have done question A. Now let's move on to the question B. We study more properties of how to work with Wiener process. Now we have expected value of W5, W4, W3, given W4. Once again, this W4 goes outside. Once again, W5 is decomposed into known and unpredictable part. W4, expected value of W4 plus, let's say I. I will be the, or delta. Delta will be W5 minus W4. Delta times W3 given W4. And this, once again, I will get W4 times, times the sum, expected value of W4 times W3 given W4 plus expected value of delta times W3 given W4. And let's make them one by one. So I will stop here and I will calculate each value separately. I will calculate each value separately. Expected value of W4 times W3 given W4, we take it out. And probably you remember how we have calculated this value. There are some ways to do this. I think the most beautiful is time inversion, but you can also do through, once again, through decomposition into two parts. The decomposition here is more tricky because that value is in the past. W3 is in the past. If I start at time t equal to 4, so basically either I should use time inversion, either I should carefully decompose into completely known part and unpredictable part, but that may be done. Let me show you the other way. So ways, I probably I know more, but I'm sure that I know two ways how to calculate it, but probably there are more ways. So, okay, what are the two ways to calculate this? The first way, time inversion. Time inversion. I say that if you have WT and you apply a special strange transformation that is equal to 0 when t is 0, and the t times W1 for t, for t bigger than 0, then this xt is also a Wiener process. This new process is also a Wiener process, and you can use assumptions of Wiener process to calculate interesting values. So that's the first idea how to solve it. So W3 will be 3 times x 1 over 3, and hence you can say that expected value of W3 given W4 will be expected value of 3 times x 1 over 3 given 4 times x 1 over 4. 3 will go outside. X 1 over 3 given x 1 over 4. But this process xt is once again a Wiener process, and it's a martingale, so it's forecasting the future given past value is its past value. So it's 3 times expected times x 1 over 4, and it will be 3 times 1 over 4 times w 1 over 1 over 4, and it will be 3 over 4 times W4. So that's the first idea. And second idea is once again, you can say that W3 decompose W3 into two parts. First part completely perfectly dependent on W4. One part that deterministically depends on W4, and the part that is independent of W4. So that may be done. So if we say that W3 is something times W4, that part completely determined by W4 plus something that can't be the part of W3 that can't be recovered from W4. So W3 can be partly recovered from the value of W4, and we decompose the W3 into two parts. So this like I don't know how to, let's write the word U, that means so that part is deterministically depends on W4, and that part independent of W4. And I can easily calculate all these parts. So how to calculate? So I calculate variance of both sides with W4. From the left side, I get covariance of W3 and W4. From the right side, I get K covariance of W4 and W4 plus covariance of U and W4. And by construction of my decomposition, I will get 3 here. I will get K times 4 there, and I will get 0 with the covariance of part that is independent of W4 and W4. Hence, K is equal to 3 or 4. So I have the decomposition that W3 is 0.75 times W4 plus unpredictable part. And if I calculate expected value of W3 given that I know W4, I will get expected value of 0.75 W4 plus U, given that I know W4, and I will get 3 over 4 times W4. I got the same answer, I hope. Yeah, I've got the same answer. So basically, we have found the answer W4 times 3 over 4 times W4. So some things with Wiener process are rather tricky to calculate, but general ideas are the same. We are decomposing some to calculate expected values easily. We decompose values into two parts. One part that is completely deterministically depends on the random variable we know, and the other part that is independent of the random variable we know, hence we can calculate conditional expected value easily. Okay, any questions? I think we are ready for more problems. Okay, let's continue. One more exercise. Point A. We have integral AT that is equal to integral of WU squared dWu, and the second integral BT that is equal to integral from 0 to T WU squared du. And the question A, calculate the expected value. Calculate the expected value. Let's go back to the properties we have stated. We have stated the property that expected value of eta's integral is just 0. And when we calculate expected value of Riemann integral, we can change the order of expectation and integration. So the first one is just 0. We are happy. That's very quick. And the second one is a little bit more tricky, but we are also happy. We just change the order of integration and expectation. Well, from 0 to T, expected value of WU squared du. Remembers the expected value of Wiener process squared. Okay, we know that WT is normal with mean 0 and variance T, hence expected value WT squared is just variance of WT, hence is just T. We don't need to subtract expected value. So it will be integral from 0 to T u du. And that's not hard to calculate. That's an ordinary integral, so it will be t squared over 2. Okay, now let's continue with variance. Point B. What is the variance of what is the variance of AT? What is the variance of AT? Once again, we use the properties we have stated. The variance of stochastic integral is just expect value of ordinary integral where the integral is squared. So using this property, I can easily calculate variance. Variance of integral from 0 to T WT squared WU dWu is expected value of integral where I square the integrated value, wu power 4 du. Hence, I have expected value of, no, I change the order of integration and expected value. It will be expected value of w power 4 times du. Now I need to calculate this thing. Okay, let's do this. There is a very interesting fact. I don't remember the name of, probably it's called Stein's lemma. Probably it's called Stein lemma. That if we have a normal distribution, if Z has standard normal distribution, or even, even I can have some expected value Z with some expected value mu and variance 1. Then if Z and h of Z is a polynomial function, then expected value of Z minus mu times h of Z is equal to expected value of h prime of Z. So when you calculate some expected value of a polynomial of a normal random variable, you can drop basically the power of a polynomial by 2 in these steps. So let's provide some examples. Okay, what is the expected value of Z power 4? So imagine that, example. Imagine that Z has normal distribution with mean 0 and variance 1. And I'd like to calculate expected value of Z power 6. Okay, what can I do? Just using it as Stein lemma. I can say that it's expected value of Z minus 0 times Z power 5. Oh, I have Z minus mu, and I have h of Z. I have Z minus mu, and I have h of Z. I just say, oh, I can remove the first term, and I can take the derivative of the second term. That's expected value of 5 Z power 4. Okay, the power dropped by 2. It was 6, now it is 4. I take out 5 and I use the same trick. 5 times expected value of Z minus 0 times Z cubed. Oh, once again I can use Stein's lemma. Z minus 0 is Z minus mu. I can completely remove it, and once again I will decrease the power of the degree of my polynomial. Yeah, so it will be 5 times 3 expected value of Z squared. Once again, I can say that this is 5 times 3 expected value Z minus 0 times Z, and it will be 5 times 3. This is Z minus mu. This is h of Z. H of Z is Z, and the derivative is easy, it's just 1. So it will be expected value of 1, and it's 15. Yeah, and you see that using Stein lemma, I can calculate quickly any expected value of any polynomial of normal random variable. I can say Z cubed, Z power 5, Z power 7. So that's not every powers are easy, even high powers, because I remove simultaneously z minus mu, that decreases the degree by 1, and I take the derivative. So in one step, I decrease the derivative by 2, and even high degrees can be quickly moved to constants, and it's easy to calculate expected value of constants. Okay, now let's go back to my case. Yeah, let's quickly prove the Stein's lemma that is very useful for calculations with normal distribution. Okay, the proof is very easy. The proof basically by integration by parts. So if I calculate expected value of z minus mu times h of z, it should be integral from minus infinity up to plus infinity, z minus mu times h of z times 1 square root of 2 pi sigma squared times exponent of minus z minus mu squared over, no, I have no sigma, it's 1 over 2 dz. And I easily see that this is, so if I take the red part, that is v prime, and that is the blue part, that will be h. So that is h, and that is v prime. And hence, by integration by part formula, I should have hv from minus infinity up to plus infinity, minus integral from minus infinity up to plus infinity h prime v dz. So that's integration by parts formula. And what is v? V will be minus 1 over square root of 2 pi exponent of minus z minus mu squared over 2. You may check that if you differentiate v, you will get exactly v prime that is written above in red, and hence this is h minus h over square root of 2 pi exponent of minus z minus mu squared over 2 from minus infinity up to plus infinity, plus integral from minus infinity up plus infinity h prime times 1 over square root of 2 pi exponent of minus z minus mu squared over 2 dz. And this is just expected value of h prime, and that is just 0 because h is polynomial and exponential function grows much faster than any polynomial. So we have completed the proof, and we can use with proud this Stein lemma that allows us to calculate quickly any expected value of any polynomial of normal distribution. So let's go back to our exercise. We need to calculate expected value of w power 4. We can say that w has normal distribution with mean 0 and variance u. So w minus 0 divided by square root of u. So my u is not very different from 4. Should write them differently. W minus 0 divided by square root of u, we may denote it by z, and has normal 0, 1 distribution. Hence, I may write that WU is just scaled standard normal distribution. So by using this scaling, I can write the expected value of U squared times Z power 4. Now I use Stein's lemma. So I write like Z minus mu times Z cube. And using this formula, I remove completely this Z minus 0. I take the derivative of Z cube. I get U squared times expected value of EZ squared. Once again, I use the same trick. It may be used with very quickly. Yeah, it's U squared times expected value of Z times 3Z. Yeah, it's something like Z minus 0 times 3Z. Once again, I use the same trick. I remove Z minus 0 and I take the derivative. And it will be U squared times expected value of 3 will be 3U squared. And now we can easily calculate expected value of any power for winner process. So now let's go back and finish our calculations here. So the end of the exercise, here we are. That's expected value from 0 to t 3u squared du. That's something like, I think, t cube. Yeah, t cube minus 0 cube. It's t cube, yeah? Yeah, I think like this. Okay, we have calculated the variance of stochastic integral. And by the way, we have learned a good lemma that simplifies calculations for high powers of standard normal distribution, and not only standard. Yeah, for example, let's provide some more examples. Okay, some more exercises on Stein lemma. Imagine that I have my process YT is T times WT plus T squared. And let's calculate the, or maybe I have in cube here. Yeah. So I have YT that is here. And let's calculate the expected value of YT. Let's calculate the variance of YT. Yeah, let's calculate the variance and the expected value of the process YT. Okay, with expected value, I think it's easy. We quickly get that it's expected value of T times WT cube plus T squared. So, T times expected value of W cube plus T squared. Probably you know that WT cube is symmetric around 0, so it's 0. Yes, 0 because WT cube is symmetric around 0. But if you don't remember this fact, so that's completely okay. You can do it with Stein lemma. We just recap that WT can be written as square root of T times Z, where Z has a normal 0, 1 distribution. So if you don't remember the fact that WT is symmetric around 0, then expected value of WT cube can be written like expected of square root of t cubed times z cube. It can be written like expected value of square root of t cubed times z minus 0 times z squared. I can use times lemma that says I should do two things at once. I should remove one factor and I should take the derivative. Will be expected value of square root of t cube times 2z, but z is normal 0, 1, so it will be 0. So I may remember the fact that something is symmetric, or I can always rely on Stein lemma. It's okay. Now let's go back to variance of yt.
Could you please show the expected?
Yeah. Sorry.
One more time, please.
Sorry, what should I show? Yeah.
Could you please show the expected value of yt? Yeah, but I have a question. How did we get the t out of the brackets? Is it a constant?
It's a constant. Be careful, the word constant has two meanings in Russian, in English, in any language, and that probably confuses you. So that is the reason we have constant may mean that doesn't change in time, and constant may mean non-stochastic, deterministic function. Yeah? In this case, if I speak about f of t that is t, or I don't know, t squared, that is a constant in the probabilistic sense. Yeah, obviously that's not a constant function if we speak in terms of calculus. Yeah, obviously if you draw the graph of this function, it goes like this. It's not a constant function in terms of calculus. Yeah, in terms of middle school, yeah, it's not horizontal line, but it's a constant in terms of probability theory. Yeah, probably that fact is confusing. It is constant in one sense, it's not constant in other sense. There are nothing random inside this function. Yeah, if I give you the specific moment of t, let's say t equal to 5, yeah, then t at time moment 5, t is equal to 5 point. And if we speak about expected value, you may take out all constants in probabilistic sense of the word constant. Yeah. So we take out of the expected value all constants that may be non-constants. They may be functions, but they should be predictable functions. We take them out of the expected value. Yeah. You see the difference? We can take constant objects that are not constant in time, but they should be constant from the point of view of randomness. Yeah, and this t squared has nothing random inside. Yeah, at time moment 4 it will be 16. At time moment 10 it will be 100, and so we can take it out of the expected value because that's a constant, not a constant function, but a non-random function. Yeah, that's okay.
Okay, thank you.
But I understand there is a confusion in the terms. Yes, we say constant. Oh, why t squared is a constant? It's not a constant. Yes, I agree that it's not constant in terms of calculus, in terms of, I don't know, middle school function plotting, yes, but it's constant in terms of probability theory, so it can be taken out. And by the same logic, we will work with so the answer here t squared. And with the same confusion, we should work with variance of yt. That will be the variance of t times wt cube plus t squared. This t squared is a constant in the sense non-random. Yeah, that's constant from in probabilistic language, yeah. So non-random. So it does not influence variance. We may remove it like a constant non-random thing, and this t will go outside. So I will have t squared times variance of wt cube. Okay, so I got t squared times expected value of wt power 6 minus expected value of wt cube squared. That value is 0 by symmetry or by Stein lemma. So it's t squared times expected value of wt power 6. And okay, we need to do this guy. Once again, I prefer to use Stein lemma standardization. I say that I recap that WT has normal distribution with mean 0 and variance t. So I can state that WT is, so if I subtract expected value divided by square root of variance, I will get Z, that is normal 0, 1. Or if I go back, I will get t squared times expected value of square root of t power 6 times z power 6. So it will be t power 5, 2 plus 3, 2 plus 3 times expected value of z minus 0 times z power 5. I see once again the Stein lemma. So t power 5 times. And the power of Stein lemma comes from the idea that I do two things at once. I take the derivative and I remove one bracket. That simplifies greatly the expression inside. So it will be 5z power 4. I do this once again, 5t power 5 times expected value of z minus 0 times z cube. It will be 5t power 4 times expected value of 3z. Z squared. And once again, 5t power 4 times expected value of z minus 0 times 3 z. And I get 5t power, power.
By power.
5. Yeah, that's my fault. Times 3. And that's 15 t power 5. Or we may easily calculate something like, let's say z has normal distribution with mean 0 and variance 1. What is the expected value of something like z power 2024? What is this value? Okay, I can quickly do this. So it will be z minus 0 times z 2023. This guy disappears. This guy I need to differentiate. So it will be expected value of z 2023 times 6 times z 22, and I see that the number above this superscript has decreased by 2, and one number has appeared as a factor, a multiplication factor. Yeah. So if I do this many times, I can do this once more. I will get one more factor, and the superscript will drop by 2. Yeah, it will be expected value of z. So basically, I will drop superscript by 2, for the price of adding one multiplier. I drop the superscript by 2, I add one multiplier, and that will continue a lot of times up to the moment when I will hit 0. So 0, I will not. I'm not hitting 0 before I hit 0. And that's the expected value of Z 2024. Okay. Now that 5 minutes, I will choose a simple exercise. No, big collection, something very simple. There's small exercise for okay. Small exercise. XT is 2017 plus t squared wt squared plus integral from 0 to t u dwu, and we will not do all the points, but point A, calculate expected value of xt, so that's point C, but nevertheless, and point A, write in a short form. So this is long form, so we should write in short form. Okay, what is the expected value? And we will not check that it's martingale. We will discuss the condition to be for a continuous time stochastic ETS process to be martingale next time. Okay, find expected value of xt. That will be expected value of xt is 2017 plus t squared times expected value of wt squared plus expected value of ETS integral, and this thing is 0. This is t, so we got 2017 plus t cube. Maybe B is xt a martingale. We can answer quickly. Xt a martingale. The necessary condition, not sufficient, but necessary condition, necessary, point C, point B, necessary condition. I stress that it's necessary, it's not sufficient. Expected value of martingale should be constant. Sufficient condition is a little bit more tough to check. Sufficient condition that expected value of mt plus delta given ft is just mt, but even necessary condition is not satisfied. Our expected value grows in time, so our xt is not a martingale. It's not a martingale. And the last question, dxt. So dxt. We know how to write integrals in short form. In short form, we write it like t times dwt. So that's the way to write integrals in short form. And we also need to write this function in a short form. And to write functions in a short form. We have Ito's lemma that describes how functions are written in short form. Yeah, we have Ito's lemma that says that if you have a function, there is a way to write it in a short form. Okay, in our case, we have h of t and wt is t squared times wt squared. Ito's lemma says that dxt is 2t times wt squared times dt plus 2wt times t squared dwt plus 1 over 2, the second derivative. It will be 2 times t squared dt. And we have also the last integral, like t dwt, and that's a short form for our xt. If it's the Ito's part, and that is the integral. Once again, all the terms are dh with respect to dt times dt plus dh with respect to dw times dwt plus 1 over 2 second derivative of h with respect to w times dt and plus short notation for the integral. Yes, the time is up. Thank you for your questions. If you have more questions, don't be shy. I think with stochastic integrals and processing continuous time, we need to have more practice and more and more. You know, that's a tough subject. I understand well that all integrals, derivatives, that's combined with expected values and variances and all probability theory. Even the word constant has two meanings now, and understand that stuff. Let's be brave. Let's solve more problems. Thank you for coming. That's all. Okay, if you have questions, don't be shy. If you have questions, then I wish you a good evening.
Thank you. Goodbye.
Bye.